different than the liquid. And so that's why we have to talk about these states of matter. And of course, that's where we're going to be going over these next couple of chapters is what is the behavior of a gas? What is the behavior of a liquid? What is the behavior of a solid? In fact, I would probably say we've covered the solids pretty well because that's what we've been doing way back with our mechanics. We've been taking a solid object like a ball and we toss it across the room here. And so you'll hear me say this, that we're probably going to spend most of our time then focusing on the physics of gases and liquids, somewhat on plasmas. We got a couple of chapters to get there before we can worry about charges. And then the solids, I would say we've pretty much already done. But I hope you're seeing the obvious pattern that the gas state of a matter, like H2O, will be at a higher temperature than the liquid, and the liquid will be at a higher temperature than the solid. And again, I keep using water because I think water is a really good one because it's very common in your life. You have gotten water cold to make it a solid. You call it ice, and then you've warmed it up and it's become a liquid. And I'm sure other times you've even put it on the stove and you've boiled it and you've watched it come up and it just kind of floats away and it kind of mixes into the air. It's not air molecules now. It's still H2O. They're just H2O on their own. And so I want to emphasize that when I'm talking about the change of state, we did not change anything from being water to something else. We didn't separate the H2O and get hydrogen or oxygen gas. That is not what we did. We just took the original H2O and semi-broke their bonds and we got a liquid H2O. Then we semi-broke their bonds and we got a gas of H2O. And so in this room, there's a lot of H2O molecules floating around. Now, not as many as oxygen and nitrogen, but there is still a lot of H2O molecules floating around here. And so I can't overemphasize this, that we're not changing the molecule itself. It's still H2O, but I am trying to emphasize that these behaviors are different, and you have to have the higher temperature for the gas than the solid. That's just because the bonds have to be broken. And so even though I keep dwelling on H2O, let me pick something that maybe is less common to you. How about I pick this 500 grams of aluminum again? Is this a solid, a liquid, or a gas? Well, I hope you're saying solid. You're saying, yeah, they're hooked together, right? You can see it keeps its shape. I can put it up like this and it keeps the same shape. I can put it in a container, if you will, would be the sink, although you can't see, but it still has its same shape. It doesn't matter if I put it on its back or on its face or on its rim, it keeps its same shape. These atoms are held together. I would say these are then, in this state, right here, they are solid. The atoms, and in this case they'd be aluminum atoms, they are held together. And if I warmed it up, what would happen is I can get a liquid. I would get a molten metal. Now that's a pretty high temperature, so I doubt if you've ever warmed up aluminum quite that hard, but maybe you have. Maybe you've seen somebody welding. Maybe you've seen videos, but it probably doesn't take too much of your imagination to say, yeah, a metal can turn into a liquid. And here's my question. What if you got it even hotter? Could you take a container of aluminum and after you warmed it up and the solid turned into a liquid, could you boil it? Could the aluminum atoms then become separated and float around the room? Which is really hard on your lungs, so let's not do it. But the answer is yes. And so even though I keep focusing on H2O, I want to emphasize that this is true for all the atoms and molecules. You can heat them up and then they break free. And so even though you may not be familiar with aluminum atoms floating around the room, rest assured they could be. And by the way, that's how all of your electronics are made too. They use this aluminum vapor to settle on your wafers of your semiconductors, and so they turn it into a gas. That's the scientists, and they put it in a container so it doesn't, go floating around the room if they're trying to control it really well. But this is a really nice aluminum, gallium arsenide layers that you'll make on your silicon wafers to make your semiconductors here. Let me go the other direction, because let's start with a gas. Again, I think most of you are familiar with things like this room, where there is nitrogen in the air. As I said, about 80% of this room is nitrogen, and so we think of nitrogen as a gas. And although that's true, what would happen if I got it really cold? Could I make it a liquid? Could nitrogen be in a liquid state? And the answer is yes. Maybe you even see this once in a while. It seems like I see it a lot on the freeway. I'm driving down the freeway and I see this big tanker truck. And on the side of it, it says liquid air. And usually it's heading down to UCSB because they use the liquid air to get things really, really cold. It would be very similar to if I had ice water. If I wanted to get something cold, I could pour ice water on, and that would get it cold down to 0 degrees Celsius. But what if I wanted to get it really, really cold? I'm talking about maybe negative 200 degrees Celsius. Perfect. If I have a container of nitrogen that is so cold it's in its liquid state, it's at about negative 200 degrees Celsius. So I can then just take a bucket and pour it on and cool it down and then run my experiments. In fact, that reminds me of one of my favorite scenes in Terminator. I think it was Terminator 2. It wasn't the first one. Pretty sure it's the second one. Maybe you guys saw it. Did you see that Liquid Man guy? Yeah, I just, you know, some things about movies I can't stand because it doesn't match physics, but this one I just loved. The first time I was watching it, it was just like, you know, Arnold Schwarzenegger was driving his motorcycle down the freeway, and by this time they've been in battle with Liquid Man for 1,000 times, and you know that the whole advantage of Liquid Man was when he pumps that shotgun and blows it right through him, it doesn't stop him, doesn't hurt him, right? The shotgun goes through, spreads the liquid out, and then it just reforms. And so the brilliance of making a Terminator out of a liquid is incredible. You just can't kill this Terminator. It's Liquid Man. And so by this time, Arnold Schwarzenegger is like, I don't know how I'm going to save, is this John Connor? And they're zipping down, or the mother of John Connor, or something like that. And so they're zipping down the freeway. He's like, God, how am I going to stop them? And then the brilliance comes in. He sees the big truck that says liquid air on the side. It's all cold to nitrogen. And he knows that if I can get that cold nitrogen onto Liquid Guy is going to get cold, and Liquid Guy is going to become Solid Guy. And when Solid Guy is now a solid, or Liquid Guy is now a solid, I can now blast him with my shotgun and he'll break into little pieces. And so as soon as he crashes into that, or makes that truck crash, I'm just like, oh, that is so brilliant. Liquid Guy is going to become a solid. The problem of him being a liquid is gone. He's now a solid. Oh, that's brilliant. And so sure enough, that's what happens. He turns into a solid, and Arnold Schwarzenegger pumps him with the shotgun, and little pieces go all over the place. And I'm like, oh, that's brilliant. And I'm thinking, okay, movie's over. Oh no, then it got even better. Because then, of course, this is the brilliance of being a liquid. It was only a solid when it was cold. Now, this gives Arnold time to escape, but Solid Guy is going to warm up and become a liquid. And so the makers and the engineers of this Liquid Man can now flow together, and Liquid Man has been reformed, and now the hunt can continue. And so that's a good example and of, well, Hollywood geniusness, but also using the properties of liquids and solids and cold temperatures and high temperatures in a sci-fi movie that I found just fascinating here. But maybe I shouldn't spend too much time on here because I think you're really getting the idea of this. But I do want to be a little careful. I want to keep going to higher temperatures and talk about plasma, but I think maybe the best way to go is to go back to a solid. How about I take a piece of chicken and I warm it up? Do I get liquid chicken? Is that how you make chicken soup? Do you make chicken soup by taking a piece of chicken and you just put it in the oven until it gets so hot it becomes a liquid? Well, of course not. What happens to a piece of chicken? Yeah, long before it gets hot enough to turn into a liquid, the molecules themselves break apart. And that's the problem with big molecules. Big molecules, you try to warm them up, they break apart. And so you're never going to get liquid chicken. What happens is you don't have chicken anymore. Chicken is made out of these very big macromolecules that have things like carbon and nitrogen and oxygen and hydrogen in them. And what ends up happening is those break apart before you ever get a liquid. So I want to be a little careful when I say everything will go from a solid to a liquid to a gas. Because although that's true for the simple molecules like H2O, like aluminum, like nitrogen, when you get to something that's a little more complex, even alcohol, let alone chicken, when you get to these high temperatures, the molecules themselves may break apart, so you don't really get them as a liquid anymore. And in the case of chicken, you separate them off, and that's what that black stuff, you'll call it burnt. You'll say, hey, I burnt my chicken. I tried to warm it up to make a liquid, and I burnt it. Yeah, because what you did is you took away everything but the carbon, and the carbon's left behind. And so all you've done is changed it from chicken to carbon. And that's the burnt chicken. So I want to be careful with that, and I say that because plasma are elements only, because again, if we go back to our H2O, if I start with very, very cold H2O and it's a solid, so it's in the freezer, and I pull it out of the freezer and I let it warm up on the kitchen table, then it becomes a liquid. Then if I take that container and I put it on the stove and I warm it up and I boil it, it turns into a gas. Now if I have a container so it can't go around the room and I hold that container and I start to warm it up even more, what begins to happen? And maybe this picture is the best picture to describe. Here's my H2O, and so if I have a bunch of H2O and I start warming it up more and more and more, it's true that the H2O will get to a gas. In other words, it will become a gas and the bonds between the molecules will break apart. That's what makes it a gas before the bonds between the H's and the O break apart. That's the problem with chicken and getting a liquid or a gas chicken. The bonds between the individual atoms break apart before the bonds between molecules break apart, and you can't get a liquid chicken. Fortunately, I can get a liquid H2O. I can even get a gas H2O, but I cannot get a plasma H2O. Because what will happen is if I take H2O and I warm it and I warm it and I warm it, the H2O hit harder and harder and harder, and eventually what happens is the O's, the oxygens, separate from the H's, the hydrogens. That is not a plasma. But sadly, I do not have H2O anymore. Now I have a container of elements, oxygen and hydrogen. A plasma then has to go even higher temperature than this, because when the electrons break off, and so you've hit this so hard that the bonds holding the electrons onto the atom break off, and so we got an electron over here, and 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 an electron over here. So when we get to a temperature that is so high that the electrons actually break off, and so what I have are pieces of charged material, what we call ions, if you remember from the last chapter, then that's a plasma. And that would only happen once you've broken all the bonds between them. So it doesn't matter what you start with. You will never get a plasma of water. You break apart the water into H2O first. Oh, by the way, a side note in recent history and a little further past history, we use water for cooling things a lot, and one of those is our nuclear reactors. And what year was that? 2011, and the tidal wave and earthquake in Japan that knocked out their nuclear power plant ended up spilling a lot of nuclear material in kind of an interesting pattern. It wasn't that the building fell apart during the earthquake. It wasn't even that the building was damaged by the tsunami. That wasn't the problem. They built it to that. That was the design. That was brilliant. But what happened is the tsunami took out all the electrical power lines leading to the power plant. And the power plant then could not run the water pumps that circulated the water. And so the water just sat on the nuclear material getting hotter and hotter and hotter and hotter. And it turned from a liquid into a gas, and then from a gas it turned into breaking apart the H's and the O's. Now, it never got so hot that it was a plasma. I'm not trying to say that. But it got to the point where the H's were separated from the O's, and then you have hydrogen and oxygen. And you remember that experiment I did with the balloon where I had the hydrogen and I lit it on fire and it exploded? Well, that's what happened inside of their container. And so they get a container that is filled with this explosive hydrogen, and right next to it is oxygen, and all it needs is a little spark or a flame, and sure enough it did. And so it exploded, and it blew off and blew apart the power plant and threw nuclear material all over the place, including into the ocean. And so it just made a mess with nuclear material all over the place. But it wasn't a nuclear reaction. It was very, very different than all of that. And so that's the difference then between those. Well, it is a good place to stop, but I'll just say here as we come to our stopping point that this is what this chapter 12 is all about. If the molecules are not held together and can freely move, or here they're just partially held together, or here they're completely held together, and even in plasma they're not held together but they're charged, then what would their behavior be? How would these things behave? And so that's what we're about to do. And so the rest of this chapter is looking at some properties. One was discovered by Bernoulli, so we've got Bernoulli's property. Another is Archimedes, and so we'll talk about Archimedes' principle. And both of those talk about if the molecules can move, and so they apply to both the liquids and the gases. But I'll call it quits for today, and hopefully for your homework, you will do this chapter 11. I need to adjust Canvas so you guys can start turning things in as we start getting ready for the test. And I'll just say again, the test is 1 week from today. And so right now I'll just say, hey, let's call it quits. We'll take a break, and I'll see you in about a half hour over in lab. All right, bye now.